Hi guys, so welcome to an introduction video on numbers. So in this session, we'll be learning about classification of numbers. So we'll understand what are the different types of numbers and how do we handle them. Right. So let's get started with the session immediately. Now, in your aptitude exams, we majorly deal with real numbers, right? So what are the two major components which come under real numbers? The first form of numbers that come under real numbers is rational numbers. Right now, what are rational numbers? Any number that can be represented in the form of p by q is called a rational number. And the second form of the numbers is called irrational number. Let's try to understand what's a rational number. By definition, it is the set of all the numbers that can be expressed in the form of p by q. Right. So therefore, uh, where p and q are integers and relatively prime to each other. So any number that I can represent in the form of p by q becomes my rational number. Right. So for example, you have 2 by 3 is a rational number which is already in the form of p by q. So p divided by q. Now I have minus 1. Is minus 1 as then is a rational number? Yes, because I can write this as minus 1 by 1. Is minus 5 a rational number? I can write this as minus 5 by 1. Is 10 a rational number? Of course, yes, I can write that in the form of 10 by 1. And is 5 by 4 a rational number? It is already in the form of p by q. Right. So any such number that I can represent in the form of p by q becomes my rational number where q is not equal to 0. Right. Similarly, what are irrational numbers? The numbers that we cannot express in the form of p by q. For example, root 2. Root two's value is 1.414 and so on, so on, so on, so on. Right. So I can't write in the form of fraction. Similarly, what is root 3? Root 3 is 1.7 something, 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 something. For that case, even pi. When we use pi, you might be confused that we use pi as 22 by 7. But please understand, 22 by 7 is an approximate value of pi. The actual value of pi is a decimal value which does not end. For that case, all the constants that we use in mathematics, they have a very, 10 to the power e concept there. So they are decimal values where their decimal values do not end. So we always have approximate value of all the constants that we use in mathematics. Right. So let's get started with the real numbers or rational numbers. So under rational numbers, we have three different forms of numbers. The first one is an integer, which is called a non-decimal value. The second one are decimal numbers, and the third one is a fractions. Right. Now let's try to understand each of them in details. Now, what are integers? Now, integers are the non-decimal numbers that I can represent on a numbers line. Right. So, for example, when I talk about integers, right? So, integers can be divided into three parts. We have negative integers. Negative integers are the numbers which range from negative infinity to minus one and which are also non-decimal values, right? So, if you ask me, if I talk about a number line, so if this is my number line, this represents negative infinity. Then you have, let's say, minus 3, minus 2, minus 1, 0. And then you have 1, 2, 3, 4, and so on, so on, so on. This ranges to positive infinity. So any non-decimal value represented on this number line is called an integer. Right. So now this set of numbers from minus infinity to minus 1 are called negative integers. Clear? Right. Now, similarly, when I go from 0 to positive infinity, okay, my whole numbers are the numbers which can range from 0 to positive infinity. Now, why from 0? Because 0 is neither a positive value nor a negative value, right? So 0 becomes a non-integral value. So this portion are all my positive numbers or which are also called positive integers. Now, it is very important for us to remember these terms, right? Similarly, including 0 till positive infinity, right, are called non-negative numbers. Right. Why is 0 involved? Because 0 is neither positive nor negative, right? So these are also called whole numbers. Whole numbers are ranging from 0 to positive infinity. Similarly, 0 is neither positive nor negative, and that is why these are called non-negative integers. Now, these three terms are really important because a lot of questions in algebra use these terms saying that x is a non-negative integer. So when I say x is a non-negative integer, which means x can also take 0. Or I might use a term called x is a positive integer. If I take x is a positive integer, then x cannot take 0 there. Right. Now let's look at positive numbers. What are positive numbers? Positive numbers are also called the natural numbers or they're also called counting numbers. Right. Now, 1 is the smallest positive integer or natural number that we know. So any number ranging from 1 to positive infinity, which is positive, and non-decimal, all these set of numbers are called positive integers or natural numbers. Positive or natural, or these are also called counting numbers. Clear? Similarly, when I talk about 0, including 0 till positive infinity, we have something called a non-negative integer, or it is also called a whole number in the whole process. Clear? Right? Now, let's try to understand what are fractions, right? So before we move forward, are integers rational numbers, right? So when we go to the previous slide, I've included integers and rational numbers because when I talk about any non-decimal value, minus 3 can be written as minus 3 by 1. When I talk about minus 2 can be written as minus 2 by 1. When I talk about 10 can be written as 10 by 1, and so on and so on and so on. So all the integers can be expressed in the form of p by q, and hence those are my rational numbers, right? Now, when I talk about fractions, are fractions rational numbers? Of course, yes, because fractions mean there is a numerator and there is a denominator. So, whenever I express fractions in the most simplified form, they can be written in the form of p by q. So, let's understand that p by q or any fraction is always a rational number. So, when I talk about proper fraction, what do we mean by proper fraction? When the numerator of the fraction is less than the denominator of the fraction, then the number is called a proper fraction. This is first identification point. And second identification point is if the numerator is less than the denominator, then the value of the fraction is always less than 1. So we have examples like 1 by 2, 3 by 4, 4 by 5, 7 by 8. All these values are less than 1. 1 by 2 is 0.5, 3 by 4 is 0.75, 4 by 5 is 0.80, and 7 by 8 would be 0.875 will be your fractional value. So what's an improper fraction? An improper fraction is a fraction where the numerator is greater than your denominator. And if the numerator is greater than the denominator, then the value of the fraction is always greater than 1. Right? For example, 3 by 2, 5 by 4, 6 by 5, 14 by 11, and so on and so on and so on. These are called improper fractions. So in short, fractions also are in the form of p by q, and thus my fractions can be termed as rational numbers. Clear? Right? Now, let's go to decimal numbers. Now, what are my decimal numbers? My decimal numbers are of two types. One is terminating decimal. Now, terminating decimals can be like the decimals which end like 2.5 and we end there. Minus 1.2, we end there. 0.3, we end there. 0.33, 0.125, and so on and so on and so on. All these are called terminating decimals. Similarly, when I talk about non-terminating, there are two types. One is the recurring decimals. Recurring means the number that keeps on repeating and does not end at all. And the other ones are non-recurring numbers, right? These are the numbers which do not repeat. So recurring numbers have a repetition trend. They repeat and they do not end. Okay. Similarly, your non-recurring numbers, they do not repeat. Like the value of root 2, 1.414 and something, 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 something. Right? So they do not repeat. But since they have the word called recurring, which means they do not end, they continue endlessly, right? So therefore, root 2, root 3, and so on, so on, so on are non-recurring numbers. Now we know that non-recurring numbers fall under the concept called irrational numbers, which means I cannot express them in the form of p by q, right? But can I express terminating decimals and recurring decimals in the form of p by q? Let's see that. Now, what is a terminating decimal? Now, terminating decimal, the decimal expansion of a by b terminates if and only if b has prime divisors in the form of 2 to the power p into 5 to the power q. What does this mean? Let's try to understand. So if I give you 1.2, if I simplify 1.2, this becomes 12 divided by 10. If I simplify this, this becomes 6 divided by 5. Right? So denominator is in the form of 5 to the power 1. Clear? Similarly, let's say I talk about 1.23 and I stop here. Clear? So 1.23 can be written as 123. Since two values are there after decimal point, so denominator will follow by double zero. Now, if you factorize your denominator, 100 can be written as 2 square into 5 square. So please understand, whenever the denominator is in the form of 2 to the power a or 5 to the power b or 2 to the power a into 5 to the power b, this number can be written as terminating decimal, right? Similarly, let's take one more example. Let's talk about 1.45. This will be written as 145, two values after decimal divided by 100. If I further simplify, this becomes 529 and this becomes 5 into 20. Now, if you simplify your denominator, 20 is 4, that is 2 square into 5 to the power 1. Right. So any fraction where the denominator is in the form of 2 to the power a into 5 to the power b can be written as a terminating decimal. Having said that, since I'm writing in the form of the numerator divided by denominator, which means this number can be written in the form of p by q. Clear? And if this number is written in the form of p by q, that means terminating decimals are also called my rational numbers. Clear, guys? So it is very clear that among decimal numbers, terminating decimals are rational numbers. Now let's get one simple question here. Now, how many positive integers less than n or equal less than n or equal to 50? How many integers positive integers n less than or equal to 50 has a fraction 1 by n, which is a terminating decimal, which means if I want 1 by n to be a terminating decimal, what is the concept of terminating decimal, guys? The concept of terminating decimal means the value of n should be in the form of 2 to the power a into 5 to the power b. Clear, right? So now what are these values? That means I want n to be in the form of 2 to the power a into 5 to the power b. And the second condition is n should be less than or equal to 50. Right? Now let's try to understand this here. So when I have this, so let's say n can always be in the form of 2 to the power 0, which means n can be 1, which is acceptable. Similarly, n can be in the form of 2 to the power 1 into 5 to the power 0 into 5 to the power 1 into 5 square. Now remember 5 square is 25, 25 into 2 is 50. So I can't continue with the 5 cube. So 2 into 1, if the denominator is 2, it is a terminating decimal. If the denominator is 10, it is a terminating decimal. If the denominator is 50, it is also a terminating decimal. Clear? Right? Now, can n take 2 square? Yes, n can take 2 square. Now, if I take 2 square, then I can again have into 5 to the power 0 into 5 to the power 1. Now, when I go with 5 square is 25. 25 into 4 becomes 100. 100 is not within our limits. We want the value of n to be less than or equal to 50. So 4 into 1, if the denominator is 4, it is a terminating decimal. Similarly, if the denominator is 4 5s are 20, it is also a terminating decimal value here. Clear? Now, can n take 2 cube? Yes, 2 cube is 8. 8 into 1 is 8. Similarly, 8 into 5 is 40. I cannot go with 5 square because 5 square is 25 and 25 into 8 becomes 25 twos are 50, 54s are 200. Clear? And 200 is not within our zone. Similarly, can n take 2 to the power 4? Yes, 2 to the power 4 into 5 to the power 0 is accepted. I cannot take 5 to the power 1 because 5 into 16 gives me 80. Similarly, 2 to the power 5 is 32. 32 into 5 to the power 0, that is 32, will be one of the values here. Clear? Now, can I take 2 to the power 6? 2 to the power 6 itself becomes 64. So I can't take 2 to the power 6. So my denominator value of n is any one among these, then 1 by n will always be a terminating decimal. So I have three values here. I have one more value here. Clear? Similarly, I have two values here. I have two values here, and I have one and one here. That means we have 1 plus 3, that is 4. 4 plus 4, that is 8. 8 plus 2, that is 10. So we have a total of 10 values. Clear? We have a total of 10 values where the denominator is in the form of 2 to the power a into 5 to the power b. Clear? And this is going to be my value. Let's take an example. If I give you 0.5, this becomes 5 by 10, or you get 1 by 2. Clear? Now, if I take 0.1, if I take 0.1, that becomes 1 by 10. So if you see, all these values are acceptable. Here, suppose I take 0.02. If I take 0.02, this becomes 2 by 100, which can be written in the form of 1 by 50. So you can see that Whenever I have a terminating decimal, the denominator is in the form of 2 to the power a into 5 to the power b. Clear? And we are getting a terminating decimal expansion. So please remember this definition of terminating decimal. That denominator should be in the form of 2 to the power p into 5 to the power q, and that will be the form of a terminating decimal. Right? Now let's move to recurring decimal or non-terminating decimals. Right? Now in non-terminating decimals, we have a non-terminating decimal has endless digits after decimal. Right? So there are two types of non-terminating number. One is a recurring or repeating. The second one is non-recurring and non-repeating. Right? So we have seen that non-recurring and non-repeating comes under the concept of irrational numbers. Right? Which means this is still a rational number. Now our job is to see that how do I convert a recurring decimal into P by Q. Now, let me tell you, we have learned this in standard 8 in school days, right? So let's try to simplify that process, right? Before that, let's understand what is a repeating decimal. Now, in repeating decimal also, we have two types. One is a pure recurring decimal. The second one is a mixed recurring decimal. Pure recurring decimal identification point is the repeating trend or the repetition starts right after the decimal point. Clear? Here we have the repetition trend. TIT, repetition is there, but not right after decimal point. Okay. Now let's see. So 0.33333. So I can write this as 0.3 bar. So if I have a bar only on 3, that means 3 is the number that keeps repeating. Similarly, 0.454545. So you see the repetition starts right after the decimal. I can have 1.2454545, sorry, 245, and so on, so on, so on. So 245 is repeating and it's repeating right after decimal points. These are called pure recurring decimals. We'll learn how to convert this in the form of P by Q, right? Similarly, a mixed recurring decimal, you can see 0.234343434. So what is happening? 2 is not repeating, but 34 is repeating. So therefore, there is a repetition trend, as well as there are some digits which are not repeating right after the decimal point. 1.23454545. So what do I see? 2, 3 are not repeating, but 4, 5 is repeating. So therefore, 1.2345 bar becomes your mixed recurring decimal, right? Now, let me tell you that these are also rational numbers. Okay. Now let's try to understand how do I convert them in the form of P by Q, right? So when I have, let's say 0.3 bar. Okay, the simplified shortcut, I'll not get into the maths part of it. The maths part of it says, if you remember the school days, let me just rewrite it for you. Let's do one mathematical calculation. So math says let x be equal to 0.33333, or let's write it as 1.333. Okay. Now, since only 1 3 is repeating, I multiply this with 10. So I write 10x is equal to 13.33333, which is repeating. Now, if I subtract both of them, what do I get? I get 13 minus 1. This part gets cancelled. Repetition part gets cancelled. And on the left-hand side, we have 9x. I repeat, I'm subtracting equation 2 with equation 1. So if 9x is equal to 13 minus 1, then we get the value of x is equal to 13 minus 1 divided by 9. Okay, now let's simplify. The simplified form is, since I have 1.3 bar, I am writing the complete number once without repetition and without decimal. Clear? Now I will subtract the portion that is not repeating. So what is not repeating here? 1 is not repeating. So I'll subtract 1 from here. Clear, guys? Now, when I come to the denominator, since only one digit is repeating, I will write 19 here. Right? So this becomes a simplified form of the pure recurring decimal. So this becomes 12 by 9. Now 12 by 9 is nothing but 4 by 3. And 4 by 3 is in the form of P by Q. Therefore, this is a rational number. Let's take one more example. Suppose I take 12.45 and the number 45 is repeating. Okay. Now let's do it together. We write the complete number once without decimal and without repetition. Okay. Now we subtract the portion that is not repeating. What is not repeating? 12 is not repeating. Therefore, I subtract 12 from here. Divided by. Now, since after decimal 2 digits are repeating, I will write 2 nines in my denominator. So this becomes the shortcut. So the numerator is complete number ones, right? Without repetition and without decimal, minus the portion that is not repeating. Clear? Now in denominator, you will have as many nines as the number of digits are repeating after decimal. Okay, guys. Now let's take one last example. Let's say I take 1.345 and the bar is on 345, which means 1.345, 345, 345, and so on, so on, so on. Okay. Now I write my complete number ones without decimal and without repetition. I subtract the portion that is not repeating, so only one is not repeating, right? Divided by, after decimal, there are 3 digits repeating, so denominator will have 3 nines, and this becomes the simplified P by Q form of a pure recurring decimal. Clear, guys? Now let's go to a mixed recurring decimal here. Now what's a mixed recurring decimal? Let's take first case. Let's say x is equal to 1.23333. Now, since 2 is not repeating, let's first multiply with 10. So we write 10x is equal to 12.33333. Now, since only one digit is repeating after decimal, I again multiply this value by 10. So 10 into 10 becomes how much, guys? 100x. Now 100x will give you 123.33333 and so on, so on, so on. The whole motive is to cancel the portion after decimal. Now, if I subtract these two, I get 100 minus 10, that is 90x is equal to 123 minus 12, or the value of x is equal to 123 minus 12 divided by 90. Clear, guys? Now, let's try to understand this. So, what is happening? I wrote the number as 1.23 bar. The numerator is not changing. I write my complete number once without decimal and without repetition. Now here, what is not repeating? 1, 2, that is 12 is not repeating. So forget the decimal here, right? So 12 is not repeating, divided by. Now for the denominator, focus about the portion after the decimal point. Okay. Now how many digits are repeating after decimal? Only one digit. So I'll write 19. How many digits are not repeating after decimal? One digit is not repeating after decimal. So therefore, this is going to be 10. So our answer here becomes 123 minus 12 divided by 90. Let's take one more example. Suppose I give you 1.2, 34, 34, 34, and so on, so on, so on. So I'll write 1.234 and the bar is on 34. So I write 1234 as a complete number once without decimal and without repetition. Clear? I subtract the portion that is not repeating. So 12 is not repeating. I repeat, forget the decimal here, guys. So 12 is not repeating. Now for denominator, focus on portion after decimal. Now how many digits are repeating after decimal? 2 digits are repeating. So I'll write 2 nines. Now how many digits are not repeating after decimal? One digit is not repeating after decimal. So I'll have 10. So the only thing that changes in the denominator is as many nines as the digits are repeating, followed by as many zeros as the digits are not repeating. And the numerator remains same as we did in the previous model. Right? So let me take one more example for you guys. So let's just take one last example and we'll have a practice of this. Don't worry. Suppose I have 1, 2.3, 4, 5, 6 and 4, 5, 6 is repeating. So I write complete number once without a decimal, without repetition, right? I subtract the portion that is not repeating. What is not repeating? 1, 2, 3 is not repeating. Divided by as many number of nines, as many digits are repeating. So how many digits are repeating after decimal? I repeat, for the denominator, you have to focus at the portion after decimal point. So after decimal, 3 digits are repeating, 3 nines, and 1 digit is not repeating. So therefore, 1 0. So this becomes your P by Q form of the mixed recurring decimal. So in short, even a mixed recurring decimal can be written in the form of P by Q. And therefore, this is also a rational number. So to sum it up, guys, this is my complete numbers tree, right? We saw that we have rational numbers, which can be written in the form of P by Q, right? Under rational numbers, we have integers. Under integers, we have non-negative integers, whole numbers, and natural numbers, which are called non-negative integers and positive integers also. Under fractions, we have pure fraction and a proper fraction and improper fraction. Proper and improper. And they are also in the form of P by Q. Now, under decimal values, we have terminating decimals. Even they can be written in the form of P by Q. And under non-terminating decimals, non-terminating and repeating can be written in the form of P by Q. And non-terminating and non-repeating cannot be written in the form of P by Q. So that is the only form of number that cannot be written in the form of P by Q, which come under the concept of irrational numbers. So it's very important for you to understand this, because sometimes the question says X belongs to rational numbers. If I'm saying rational numbers, right? So then you need to understand that it comes from this box. A rational number can be an integer, it can be a fraction, it can be a recurring decimal also, right? So that's it from this first section on classification of numbers. I hope you learned something about different types of numbers. In the next video, we'll practice how to convert recurring decimals into P by Q. We'll do a few questions on that, and we'll also practice a few questions on integers. So stay tuned for the next session. Thank you, guys. All the best.